All right, this is Mr. McMurray. I'll say welcome again because I made a video this morning and I played some music, a Weird Al song called Word Crimes, and I posted it, put it on the web page, all that good stuff. It was all ready to go, and I get a email from YouTube that says, because I'm using copyrighted material from Blurred Lines, which is what he was making a takeoff on, mine has been blocked. So, anyhow, that's how my day started. This is our second try without any music playing that we're going to try here, and we're going to do these momentum notes. Okay, I may backtrack a little bit here with the earlier notes, but that's okay. All right. We're going to talk about momentum when things collide. For example, here we have a train car that collides into one that's just sitting there, and then both of them start moving down the way. Okay, so that would be an example of a collision. Car crashes. A pool game where you hit the cue ball, it hits all the numbered balls and break at the beginning of the pool game. All those kind of things. Those are all collisions. Okay, and so let's talk about some collisions here. First of all, the total momentum is conserved. All right. And for example, here, let's just say that this train car weighs 1 ton. This one also weighs 1 ton. Okay, so 10 times 1, the momentum of this one, if it's going 10, say miles per hour, times 1 ton, is going to be 10 units of momentum, right? This one, on the other hand, weighs a ton, but it's times the velocity, which is 0, so it has no momentum. So the total momentum for the whole system would be 10 plus 0, or 10. Okay, now once this hits it, it collides, it connects to it, which makes it an inelastic collision. We'll talk more about that in a minute. Now you have 2 tons of train, because there's a ton here and a ton here, 2 tons, but they're only going half as fast. So now they're going 5 miles per hour. So 2 times 5 gives you 10 units of momentum again. Okay, and so basically that's what we're kind of saying. In a collision, now, this one was moving at 10, this one wasn't moving at all. Now they're both moving at a different speed than either were before. But even though it's not saying that each one's momentum will stay the same, each object that's in the collision, but that the total momentum of all the objects will stay the same. And so we write that as the net momentum. In other words, that's when you add or subtract all the different objects, in this case, the 2 train cars. Okay, their net before the collision will equal the net momentum after the collision, kind of like the cannonball and the cannon that we talked about earlier. Now, elastic collisions are when objects collide and they do not change shape or permanently deformed. Okay, that sounds bad. It would be permanently deformed, but anyhow, they don't change the shape of the object and they do not generate heat. In other words, we would say that they bounce perfectly. Okay, they completely perfectly bounce without changing shape and without generating heat. Now, most things, if they collide, are going to do one or the other. Okay, in fact, maybe both. All right. If you hit a golf ball, if you look at the golf ball in slow motion, you can see that this side of the golf ball is now flat, or at least the shape of the straight line there where it hits the club. So it does deform, but as soon as it bounces off and the club lets go of it, quits exerting the force, then it will go back to its regular shape. So the golf ball would hit the first part. It's not permanently deformed, but it would generate some heat. It would also generate some sound and other energy. So some of it would be lost to other types of energy. So technically, it's not what we call a perfectly elastic collision, but it's pretty close. Okay, and most balls that we hit, tennis balls, squash balls, racket balls, golf balls, are going to be like that. They are not permanently deformed, but they do generate some heat. So they're not perfectly elastic, but they're pretty doggone close. In the everyday world, there are no collisions that are perfectly elastic, and there are no collisions that are perfectly inelastic, which we'll talk about in a minute. Usually there's kind of in between. So we'll say this collision is more elastic or mostly elastic. So generally we just say this is an elastic collision because it's more elastic than inelastic, or this one's inelastic because it's more like an inelastic than an elastic one, okay? In the real world, most things fall somewhere in between there. Now, there's an exception to that, and that is on the atomic level. All right, if you have this atom and it runs into this atom, okay, it can stop and that one keeps moving. And it doesn't deform the atom, and because the outside of each atom is electrons. And what kind of charge do electrons have? They're negative. If this one's negative and this one's negative, they're going to repel each other, just like two magnets where you have south to south pole and you're trying to push them together, they will repel each other. And so when this one hits that one, it will do so without ever actually touching that one. Therefore, it's not going to change shape and it's not going to generate heat, and it would be a perfectly elastic collision. Okay, these are just other examples. They could come together and they might hit and bounce off in opposite directions, but technically they would not ever actually touch, okay, because of that repelling of the electrons, or the repulsion force of the electrons. Okay, all right, so anyhow, those are all elastic collisions. So the only perfectly elastic collisions occur at the atomic level, where molecules always collide elastically because their electrons repel each other and they never actually touch each other. All right, now let's talk about inelastic collisions. All right, if elastic collisions are when they perfectly bounce apart, inelastic collisions are when both objects stick together or become entangled. Okay, when two cars crash into each other, they don't really stick together, but they do become part of each other sometimes and stick together. All right, and so this would be an example. We have some truck crashes here. We have a truck here, A, and truck B. All right, they're going to come together, smash in the middle, and stop. Okay, so that would be considered inelastic because they are sticking together or entangled. All right, if you have a B and here A is tailgating behind it, and all of a sudden it rams them from behind, if they stay connected, then that's going to be considered an inelastic collision. All right, now the question is, which are car crashes? Well, it depends. Most car crashes, they do kind of stick together, at least for a little bit, but sometimes they separate. Okay, so sometimes they just completely, like these two trucks, they kind of crash into each other and they don't even come apart at all. Okay, so it's definitely inelastic. But depending on it, sometimes they will glance off of each other and bounce off, and that would be more of an elastic collision. But needless to say, they are not going to be, they are going to be permanently deformed, and it will probably generate some heat as well as sound and whatever else. And so it just depends on the collision, on the particular cars and how they hit each other, whether it's elastic or inelastic. It could be both. Okay, but anytime they stick together, that is considered inelastic. All right. I think that's about it. Basically, elastic, inelastic. Elastic, they bounce apart. Inelastic, they stay stuck together. All right, and either way, it doesn't matter. Either way, the total amount of momentum is conserved. Just for example, let's looking up here. When these two hit together, well, once again, let's say this is a 1-ton truck. So 1 times 10, it has 10 units of momentum. This one is, sorry, I was looking at the one above it. Okay, it also has, let's say, 1 ton, and say it has a momentum of 10. Well, we add that together, 10 plus, oh, but this one's going the opposite direction, so it would be 10 plus negative 10. So the momentum is 0. Net momentum is 0. After they smash together, guess what? Their momentum is still 0. So the net momentum does not change. Does the momentum of each truck change? Yes. Each one of them had 10 units of momentum. Now both of them have 0. But the net, or the difference between them, is the same. 10 minus 10 is 0. 0 plus minus 0 is still 0. All right. Same thing over here. You have this truck going faster than this thing. They're going to hit each other. So now they're stuck together. So you have twice as much mass, but their speed is going to be somewhere between how fast this one was going and how fast that one was going. So their velocity has decreased enough to keep them at the same amount of momentum. All right. So either kind, elastic or inelastic, both are going to conserve the total or net amount of momentum. All right. That's it. Hopefully this one will be accepted by the YouTube people, and hopefully you will get to see it. All right. Have a great day.